Let me know when you can see my screen.
Okay. I can see your screen.
Okay, that's great. So I think we Blessing has said it all, giving us recap of what we did last time. So just to still add, so that we can have like a better perspective. So because of time constraints, we are still going to like wrap up everything about PVT in terms of the explanations and in terms of some how everything is done around PVT. Then we will be having a dedicated session, possibly 1 hour, because doing that there is a lot of job. So doing that we need enough time and a fresh start to do that. So we are going to have another session after now to have a hands-on, whereby the hands-on will involve using Microsoft Excel to analyze a typical PVT report, do the extraction, you wouldn't want to miss. I think based on this agenda for the entire PVT class, we have done one, which is the overview of the PVT analysis. Then we started, like our class ended around review of key PVT parameters. Yeah, so I think where we stopped was around trying to show you the trends and experimental, like in the experimental I stopped one better explain them and have a better understanding. Complete model, which is the sources of PVT parameter. Then I'll walk us through a workflow of carrying out a PVT analysis, especially when it has to do with working with typical PVT report, so that in our hands-on session, we won't be having any need for slides again. We just be working with Excel. Okay, so I think at this point we'll be analyzing each PVT parameter one after the other, and it will do us good to understand them very well, because a good understanding of these things with analysis, analyzing PVT parameters as it pertains to reservoir calculations and estimates, you will find the physics behind each explanation very, very helpful to you. Okay, so let's just start with the first one, which is the crude oil API gravity. So just leave API for now. Let's talk about oil density. So, and when we be talking, we'll be making references to our ordinary level physics and chemistry, right? So we define density as mass over volume, right? So that's exactly how we try to understand our oil. We want to know its density, right? So when we are able to have the weight of our crude oil sample divided by the volume that we have actually gotten, then we can now estimate the density. However, this density is not really tied to a reference point. Remember, we have different crude oil samples in different locations, right? Different locations with varying parameters. We need to always tie them to a reference. That's why the industry we usually make use of API generally to estimate for oil density, right? So what API is just this. API tries to relate the density of oil with that of water. However, before you get your API, you must first of all calculate your specific oil gravity, which is the density of your oil to that of um water. So we are tying our crude oil sample to that of water, right? So once you're able to calculate your specific oil gravity over here, just looking at this equation. Okay, let me get my pen. So looking at this equation, this one you are seeing here now, this is your specific gravity, right? And this specific gravity is the density of your oil to that of water, right? So once you have done that, once you insert it here, you have your API. And how API works is that uh, the higher the API value, right, the less dense the oil is. So API that are having higher values are lighter as of compared to an API that has lesser uh, values, right? So um, let's just leave it at that for now so that I won't go too in depth. So let's just look at a typical trend of how oil density goes with respect to pressure. And it will do you good to always understand it that all our PVT parameters are pressure dependent. They are pressure dependent. Either they are pressure dependent directly or they are pressure dependent indirectly. Okay, when we come to such cases, when we'll be looking at black oil modeling and correlations, I think if I can record that, I will relate it to us. But all of them are basically dependent on pressure. That's why when we are plotting, we usually plot the parameters at the y-axis, then against the pressure at the x-axis. Okay, so this first instance, whether I indicate it in any of the plots or not, usually describes our initial pressure, right? Which is what we can refer as our pressure, reservoir pressure, right? So for density, how does it work? At reservoir condition, it is more dense, like above the bubble pressure. You know, this the bubble point, like the saturation point, right? This is the reservoir pressure. So above the bubble point, the oil is dense, is just in the single phase, right? So it will be denser when you have gases, obviously, when you have gases inside it, right? So, and I want us to recall from Boyle's law we did in chemistry, right? They they actually told us that if Boyle's law actually states that if you keep temperature constant, that your pressure is inversely proportional to your volume, right? When temperature is kept constant. So this informs us that as you increase the pressure, the volume of something will reduce, right? The volume of the fluid in question will reduce. Then if you drop the pressure, the volume, there will be increase in volume, right? In this case, I want us to be thinking of gas as behaving this way. So at initial condition, the single phase region, the oil density is starts at a very higher level, right? Then as we drop down pressure, or as pressure drops down, the volume of gas sees kind of enough space within the fluid to expand. So expansion, which is increase in volume, happens as pressure declines. So that's why you notice that. And you know, when there is a kind of increase in uh, uh, an expansion of gas within the oil, that gas has a way of lightening up the oil system. That's why as pressure drops, you notice that the the density will be dropping down to this bubble point area. At this bubble point, which is a very critical point, you notice that the gases have actually most likely somewhere around below the bubble point has actually reached its critical stage. It now goes off. It evolves off from the oil. As soon as it leaves the oil or as soon as gas escapes, for each pressure drop, you now notice that oil density will increase. And why is it increasing? The gases that are leaving will be leaving with the lighter components, right? We'll be leaving with the lighter components of the crude oil sample. That's why something like this happens. So always take note of this. And why we see these images is a typical case. At times when working with real data, it may not really follow this way you are seeing it, but it must follow a trend. It must show you something that looks like this. So what we do is that when we see a typical real life data and make the visualization, our eyes, we are always on the lookout to check whether that trend is going. If that trend is not going that way, we can now raise an alarm. Okay, so that's for oil API gravity. So another parameter, PVT parameter that is of utmost importance to us is called the gas solubility. Some call it the solution gas oil ratio, right? Some call it ROS, right? Depending. So it has different names, but always make sure you know the one we are talking about, right? So we have ROS. We have ROS. We have RSI. Then we have ROP, right? So whenever we are talking about this thing, make sure you know the one we are talking about, right? If we mention RSI, we are looking at the dissolved gas at initial condition, right? So when we mention RS, we are looking at still talking about dissolved, right? But maybe it may not really be at as early as initial conditions, right? While when we are talking about ROP, what we are talking about now we are now at the surface analyzing the amount of gas that has escaped, right? And the with respect to the volume we actually withdrew from that oil. So it's more of a production kind of parameter, right? Remember, what we are trying to do is that we want to evaluate parameters of our crude oil sample, which will give us a representation of what our crude oil is under the prevailing reservoir pressure and temperature, right? So the unit is curve per stored barrel. So you are correct. This for gas are standard conditions, and this oil, right, still are standard conditions. So solubility trend, how does this thing work? It goes this way, like the pressure behavior. It goes this way. Obviously, there's an assumption. So we make an assumption that under unsaturated, so I told you that, sorry, this is not straight, but I told you that we usually assume this to be initial, right? We assume that from initial down to the bubble point, that the ROS is usually constant. We say it's constant or fairly constant. And why are we making that assumption? We make that assumption because ROS on its own, by definition, is actually a ratio of gas dissolved in a liquid sample to the volume of that liquid sample. Now, if this sample is undersaturated, that's in single phase, obviously there's no gas. So that ratio won't work at all. So that's why it's usually kept constant down to the bubble point. It's now at bubble point, we can now start estimating. So if you notice, for each pressure drop, our ROS will be dropping. Now the question will now be, why is ROS dropping? ROS is dropping because ROS calculates or relates the amount of volume dissolved in oil to that of the volume of the oil. So after the bubble point, the gases will be escaping, and as the gases keep on escaping, the volume of gas remaining in that oil will be dropping. So that's why it follows this trend. Okay, so solubility constant above bubble point, then gas evolution below the bubble point, gas escapes and pressure drops, then oil type effects. So lighter oils have higher gas solubility and solution gas oil ratio. Okay, so this equally something we need to take note of, and these things are like the key ones. So when the ROS values are higher, you know that we are having um, lighter oils. We are dealing with lighter oils, right? So these are some of the things we need to take note of. So the formula you are seeing here, as I have explained, this is simply just the volume of gas at given reservoir pressure and temperature over the volume of oil at standard conditions. Okay, so once we make this relationship, once we use this relationship, we can estimate our RS. When we are talking about the various PVT experiments, I will still bring up this to inform us how it's being estimated in the lab. So another one that is very important is isothermal compressibility of oil. This one is a key parameter that is used in material balance calculations, used in some other calculations that involves pressure changes uh, and volume changes of our crude oil samples is a key parameter. So, and beyond oil and gas, even in general in thermodynamics, you still see this guy playing part in one way or the other. And we usually call it when we want to measure change in volume with respect to pressure, compressibility must be there. Okay, so isothermal compressibility is a measure of the instantaneous relative volume change of a fluid or solid as a response to a pressure change at constant temperature. So what it does is this, looking at this formula now, this is the volume, right? Then this is the change. So what happens is that I usually like using a kind of balloon. So pardon me. Yeah. So let's call this balloon. This is the original volume V1, right? So if there's a pressure change and remember at this initial stage plus we have plus gas. Okay. So we have plus gas. Okay. So this remember that this thing we are talking about this oil, right? So when gases will be leaving, you notice there will be a change. It's the same bottle, right? But there will be a change in volume, right? So the volume will drop because it's no longer complete. Something has left it. So what actually tries to help us to calculate uh, the volume change from this point where we have the gases to here where we have minus gas, right? So we have removed the gases. What helps us in estimating that is our compressibility. So because we are interested in oil, we now have it to be CO, which is the oil compressibility. So as this volume, where this one you are seeing here now, this VO is the volume of the fluid, why this guy measures the density, the volume change, and this one measures the density. Both of them is just like the slope, right? So when this slope is what helps us to measure the change in terms of the volume with respect to the pressure, right? Then when you multiply the effect of that change on your volume, right, you will now get the effect of compressibility, right? So how we calculate this in the lab is that let's say we want to calculate CO, right? We want to calculate CO at volume 2, right? What we do is simply we come over here and do V2, V1 minus V2, right? Which is the original volume minus the current volume all over P1 minus P2, right? Then once we are done doing that, we now divide by V2 of interest. So if you do this for each pressure intervals, you'll be able to calculate your compressibility value. So how does this thing change? So as pressure drops, right, uh, our compressibility value, oil compressibility will be increasing because as pressure is being dropped, the gases will be expanding a little, right, prior to the bulk point. So as gas is expanding a little, trying to leave the oil, the compressibility is actually targeting only the oil. Don't forget that only the oil, right? That's why you notice a slight increase in compressibility value. As soon as we hit the saturation point and gases escape, it's just like when you are compressing a balloon, the compressibility effect will just shoot off from this stand down to this stand and increase rapidly. So that's how it works. And okay, in calculations, we still see them. So another parameter that is of great importance too is the oil formation volume factor. So in simple terms, just see formation volume factor. Anytime they mention it, be it oil, be it gas, always see it as a conversion factor that tries to relate what this thing will be, what will this volume be in this condition with respect to the other condition, how will volume change, right? So we call it the ratio of oil volume at reservoir conditions to stop-down conditions. So what it actually tells us is it relates the volume of reservoir to what we can get at standard conditions. And if, for example, we have 20 barrels, right? We have 20 barrels of oil at reservoir condition. It tries to tell us, inform us, these 20, how many of these 20 can we recover at standard condition at the surface? That's what we mean by standard condition. How many of these 20 barrels can we recover? So it can be possible that we can recover, let's say 11. So 11 barrels. That's why when we divide this 20 by 11 now, you'll be seeing 1 point. That's why in most cases, you will always see BO values ranging in 1 point, especially for black oil. Then if you are talking about volatile oil, you can even see them climbing up to, let's say, 1.9 to 2 points and thereabout. Then the more the lighter oil, you can see higher values for BO. So how does this BO behave with respect to pressure? So it attends at the reservoir conditions, it's usually a little bit lower than when it is the bubble point. So it starts here, all right? Remember what this thing is measuring, let's relate it to the formula, is the reservoir volume to that of the stock tank, right? So, so when we are dropping the reservoir pressure, dropping it, as gas expands, right? As gas expands, you notice that the volume we have at the reservoir as we are approaching down to the saturation point will be increased, right? Because as of this, prior to this time, gases have not actually left, so it stay part of the fluid in the reservoir. So as we are dropping the pressure because of expansion, our BO value will increase a little. But once we hit this critical point, this saturation point, you notice that the gases will evolve. So as the gases are evolving, plus the lighter crude, you notice that the volume we have at the standard condition will be increasing. And because it's increasing, when you now do this division, you'll be getting lower value for your BO. That's why once it reaches this point, it starts to drop. So this is how it typically behaves, right? But there could be some changes too. And another truth is that BO can never be zero, right? BO value can never be zero. If BO value is zero, it suggests something to us that there is something wrong somewhere, because what you are saying is that we are withdrawing more at the surface than what we have in the reservoir. And you know now, in the law of physics, your source must be greater than the output. You can't have an output that is greater than your source. It means that there is something wrong in the volumetric calculation. So another one we have here is the gas formation volume factor, right? This gas formation volume factor, as you can see from the share I've explained, it is still a conversion factor, right? That consider volume of the gas at reservoir condition to what we have it at standard conditions, right? So But the unique thing about it when it has to do with the trend line is that it starts at the bubble point. So for most of us that have studied, that should be Tarek 𝐸𝐵𝐸. So for those of us that have studied PVT analysis, chapter 2 of 𝐸𝐵𝐸, notice that he didn't actually label this indicates this to be bubble point. So I think I've been in an interview whereby we asked someone to draw a trend for BG and the person did that. Then we are now asking the person identify the bubble point. The person, I think the person came over here and drew something like this, trying to give without knowing that once it's gas formation volume factor, you can't even have gas formation volume factor without the reservoir pressure starting from being equal to your bubble point or less than your bubble point, because that's the point where gases that you want to even use for your estimation or for your calculation will be coming out from. So there are two ways of doing this. Either you estimate it from your differential liberation experiment, or you make use of your molecular, like your fluid compositional analysis method, whereby, as you can see, you have your Z factor here, right? Then you have a temperature and pressure. You can always estimate it and validate your answer too. Then for oil viscosity, this one is the one that behaves just like the density, right? It behaves just like the density. So at initial condition is fairly high, but as gases expand due to pressure decline, you notice that the gases will lighten up the crude. And viscosity is a measure of how if a fluid can flow, right? It's a measure of ease for a fluid to flow. So as we have gases within the system, you notice that the oil will flow and be very free to flow. That's why you notice that the oil viscosity will be dropping a little because of the gas that are expanding within it. But once we get to the saturation point, what you notice that the gases will leave, and as soon as the gases leave, you are having an oil that is having lesser amount of gases in it. It will keep on climbing that way until it becomes more like a dead oil. A dead oil is an oil that doesn't have gas dissolved in it, which in most cases some people will argue, but that's just like a theoretical case for the example I'm giving. So this is how oil viscosity works. So be very careful with it and density. Both of them follow the same trend, almost like the same trend, but always be careful to identify their differences. Okay, yeah. So after reviewing those parameters, let's now look at what are the sources of PVT data. So these three you are seeing on the screen now are typical ways of getting them. There are many other ways of getting PVT parameters. So we have the lab, which is the first one, right? We have the black oil, we have the compositional analysis. We equally have one we call the analogous method. The analogous method, you may not really come across it in some texts, except you are reading deeply in WRFM or reservoir studies books, like industry focused books. That's where you see it. It's actually popular in practice than in classroom knowledge setting. Okay, so analogous method is just we are trying to estimate what our PVT parameters will be for a given reservoir with respect to its position in other reservoirs in that field. Okay, so what we are doing is just like in maths, there's something we call interpolation. So when you have a point at point A and point C, and you need to get point in between them, which is point B, you can do interpolation, right? With respect to the offset letters, you can do interpolation. That's exactly what the analogous method does, works. And in subsurface studies, a common parameter there is depth. So their location in depth can be a reference point for us to do all those interpolation and extrapolation to estimate our crude oil PVT parameter. That's the analogous method. But these three are usually like key and typical methods. So in the laboratory experiments, we have discussed this. We get the samples either downhole or at the surface. We do surface recombination or we collect at the wellhead, depending. We now carry out some experiments. Once we carry out those experiments, we can now estimate the various PVT parameters. We can determine our BO, RS, viscosity, density, and all those parameters you saw that we discussed, right? Then there are still some cases where PVT, our laboratory experiment, will just provide us with little points that may not be enough for us to make some estimates. Another thing can equally be the laboratory experiment is usually done at different pressure steps. So what that suggests, like a constraint that suggests intuitively, is that we are at the mercy of the pressure graduation of those tools they are using in the lab. And in real life, there could be a calculation, an estimate, a forecast we want to do that will be dependent on a pressure point that is not that was not captured within the lab. And if we need something like that, then it becomes something serious, right? It can equally be a case whereby we have some data points, PVT data points from different areas within the same within the same field, but we don't really trust them to use them. We can equally aggregate all of them and do a kind of modeling. So we have what we call the black oil modeling. This is just simply correlations that have been developed. Some of them are regression based, some of them are linear, some of them are non-linear, that have been developed with various crude oil samples and tested and validated. So what we do is that we get our lab data, PVT data, extracted PVT data, and we use them to build our PVT model, carry out some matching to have an accurate model. Then we can now use it and predict our various PVT parameters at any desired condition as far as it falls within the constraints, like the boundary of that model. Then we have the compositional analysis method. Now, the lab and the black modeling that I have been talking about, especially the lab, we have been talking about describing fluid samples. If you observe those lab experiments, okay, I think I'm yet to even enter to the lab experiment. All those lab experiments I'll be talking about now is just to, all those experiments are done in terms of analyzing either the volume change or the change of the volume of our fluid sample with respect to pressure, right? And we now measure those changes, capturing them using our various PVT parameters, BO, RS, and the like. None of those experiments actually, none of those studies actually studies the internal components or makes use of the internal components of those fluid oil sample. But in compositional analysis, EOS, with this where we make use of the information, we consider the characteristics, the behavior of the internal components of the crude oil sample. So if we now know that, that's equally where we do all these molecular calculations. For example, in chapter 1 of 𝐟𝐵𝐫𝐞𝐜𝐭𝐢𝐨 and some other places where they make some estimates, molecular estimates and calculations, you see some things like that. You see some things like that, and you'll be wondering, why are we having C7, C1, C2, C3? What's the need? They will tell you the molecular mass and all of that. It's under equation of states. That's where we see them. We now make use of some state equations, Rayleigh-Kwong and Penn-Robinson equations to do some modeling and characterization. Is equally another good source of another good source for our PVT data as well. So let's walk through the various laboratory experiments that we have. So the first, there are many experiments, and I need to still state it clearly. So in generally, we have three three key experiments that we do in the lab, right? So we have three key experiments that we do in the lab. So the first one is called the primary, right? The primary. So the primary experiments are those experiments that we usually take in the field, right? It can be we want to calculate the ROP, that's the produce gas oil ratio, or we want to check the density of the oil we are predicting or we are producing, or we want to confirm something from that well that we are producing from, right? Those kind of experiments, lab experiments, are called uh, primary experiments, right? Then after those kind of experiments, we have the ones we call routine experiments. Those routine experiments are those experiments that we actually perform even prior before producing from that well. That's when we want to actually analyze our fluid samples, study our reservoir components, understand our PVT parameters, and those kind of experiments, they involve the constant composition experiment, the differential liberation experiment, the separator test experiment, the constant volume depletion experiment, and many other experiments that we can capture under the routine based. Then the third kind of experiment, laboratory experiment we can have is the one we call specialized kind of experiment. Those experiments are usually done when an uh, intervention recommendation wants to be implemented. For example, if we recommend a well to be a candidate for gas injection, or if we recommend a well to be a candidate for water flooding or gas flooding or whatever, you can't just go and start carrying out that action. You must collect your fluid samples and perform some specialized kind of experiment. That's where you'll be hearing things like slim tube test and some other tests, right? Those are specialized because you want to test the integrity of your reservoir fluid and everything before you can implement some external influences to it. So with that being said, let's just go ahead. Let's just go ahead. Let me get my eraser and clean up this. So let's just go ahead and study our individual PVT experiment. Okay. So the first experiment is the constant composition expansion test, the CCE. And how does this test work? This test works, firstly, we have a crude oil sample that we have inserted in our cell, right? Now this cell, we usually, we and this oil we are inserting in this cell must be in single phase, right? When we insert it here, we make sure that we provide a pressure to it, because any drop in pressure as you insert this oil, you are actually giving room for gas to evolve, and that's not what we want. So we usually start by providing a pressure to pressurizing this oil to be above the bubble point. So that's key. We make sure that the crude oil sample, like the oil we are inserting in this cell, is at above the bubble point. So we make use of mercury or any other um, element or gas to provide support. It can be nitrogen to provide kind of support or to provide pressure to this oil, right? And the whole idea of constant composite expansion is that we want to determine our saturation point. So it's a key experiment that must be done, because if we don't know our saturation point, every other experiment we are doing will be baseless, because saturation point is a reference point, a critical point that once you miss it, you can't actually make an informed decision. So once we pressurize this oil now, and how it's done is that the bubble point pressure, let's say the bubble point pressure is at 12 o'clock, so I will be using time to denote that. Let's assume that the bubble point pressure is at 12 o'clock, right? So we make sure we even pressurize that oil above that. So these are around, let's say, 4 p.m., right? So we pressurize it down to this point whereby we know that the pressure in the cell is far greater than the bubble point pressure. And if you check, the oil is 100% oil, right? The volume is 100% volume of oil. Then at step B, we now start decreasing the pressure. Now we have moved the pressure from 4 p.m. down to around 1 p.m., right? It's still 100% oil. Then we now decrease the pressure again, right, down to the point, maybe roughly down to 12 or slightly before 12. Now, that 12 we are hitting is the saturation point, and we define saturation point or saturation pressure as the highest pressure at which the first bubble of gas can be seen, right, can escape the oil phase, the single phase, right? So if you check it, roughly 100%, and this roughly means that there are some traces of gas that must have appeared, right? Then when we drop the pressure slightly below 12, maybe around 11 a.m., you are now seeing that this volume of oil is now a little bit lower than 100%. Then we keep on dropping it till we notice like a very visible gas volume within the last cell. Then remember, all these things are done in different pressure steps. So it's the pressure step can be up to 15, can be up to 16, depending on thereabout. So that's how we do it. Now take note, because it's constant composition, it means that nothing leaves, nothing enters, right? So no fluid, additional fluid is entering, no additional fluid is escaping. So everything is inside there. Why? Because we are interested in determining bubble point pressure. So at this pressure now, whereby the first bubble of gas has been noticed, automatically becomes our bubble point or saturation point pressure. So, and for the constant composition expansion test, some of the key parameters we can discover from it is number one, the saturation point. That's the one we can determine from it. Then we have the next one, oil compressibility. You can equally determine it from that as well. Then we have the oil density. We can determine it from this experiment as well. Then the next experiment will be the differential libration expansion test. And how does this work? It works similar to the whole dropping in pressure level, but with its own unique characteristics. Okay, someone talking. Please try and mute yourself if you're not talking. So it has its own unique characteristics, right? So the idea is that what differential libration expansion test wants to achieve is that it wants to analyze the behavior of our crude oil from saturation point down to maybe at the surface condition, whereby we know that all the gases, we are sure the gases must have left, right? So we want to model that scenario from the saturation point down to the point where we are sure that all the gases must have evolved from the oil. So we want to see what's the behavior of our oil. So you notice that the starting point of this guy, although didn't start with 100% oil, but we make sure that it starts from the bubble point pressure. That's when we start paying attention to it. So we initially increase the pressurize it, like you can still see some mercury gas pressure support. So we pressurize it to be slightly above the bubble point, right? Then we now take another step and start observing how gases will be evolving. But once, according to the name libration, so what happens is that once for each pressure step of interest, for each volume of gas that has actually evolved from the oil, we flash it off. Flash it off is just like removing it from the system. But as we remove it, we equally measure the volume of gas. So remember, we discussed something around RS being the volume of gas to that of oil. Are you seeing how we can now estimate the volume of gas and relate it to the volume of oil that we have placed? Then bubble point, we said bubble point is the volume of oil at reservoir condition to that at stock tank condition. So in differential liberation, how it works is this. The volume of oil that we want to bring into the system, into the cell, right, for experiments, that volume we regard it to be the one at reservoir condition. So we keep it, we take note of it, then keep on removing the gases, till we get what we call the residual oil, and that's the VL here. I don't know if you can see it, the VL that you are seeing here, that becomes our residual oil volume. So that initial volume, which is the one we regard as standard condition, once we divide it with this final or residual volume, we now can estimate our BO. And that's likewise the same way we can estimate all others as well. So this is how the differential liberation works. We just keep on dropping and measuring volume of gas, residual oil, then we flash, we keep on dropping, and we keep on doing it until we observe that no reasonable amount of gas is coming out. And again, we have attained our standard condition. And if you can remember, our standard condition are usually condition whereby we have 14.7 psi and 60 degrees Fahrenheit in terms of temperature. Okay, then for the last test that is still key is the separator test. So the separator test, in as much as it starts from the saturation point, it has its own purpose, and its own purpose for separator test is that we are interested in determining the separators we are going to deploy for production from that reservoir. Okay, so we need to determine our optimum separator conditions so that when we are doing our field development planning in a more robust sense, we have a good setup and a good recommendation for our separator conditions, which will be very fit for the crude oil sample we are producing. Okay, so the purpose of separator condition is simply this, right? We want to achieve three things, and those three things is something we need to take note of. An optimum separator condition, we define it as a condition that gives us the minimum RS, the minimum BO, and the maximum API. Okay, so, and we have our reasons for these three. Okay, so RS and BO tries to measure a change of something at reservoir to that at standard condition. RS is telling us the volume of gas dissolved in oil, right? Then BO is telling us the volume of oil at reservoir to that at the standard condition. You now notice that both of them, the higher their value means that the less amount we are going to make at the surface, and that's not the whole idea. So we need to find that separator condition that will minimize this rapid change, or this that will reduce this ratio of what we have in the reservoir to what we have at the surface. So that's why we need that separator condition optimum for minimum RS and BO. Why for API? We need the one that is maximum. In as much as we want to, the whole idea is to make money, right? So we make sure that we go out for those API those separator conditions that will give us higher API, in the sense that, remember, the higher the API value, the lighter the crude. We wouldn't want to waste our money trying to produce from a heavy crude oil, while we can invest the same amount and get from a higher, make like a higher production from a lighter crude oil sample. So that's it for this. Then there are equally some instances where we need to, I think that's where we do PVT correction, whereby we want to actually correct the differential liberation to separator condition. So separator condition has few pressure steps, right? It has few pressure steps. Differential liberation can be up to 15. Separator can be step of, let's say, 2, 3, 4, or 5. Right? It doesn't really meet up. So, and you know, reservoir separator condition is just like the final condition of interest, right? So we need to correct these are differential liberation and match it to that separator condition, right? So that's still it for now, but I believe when we are doing a hands-on, we can equally buttress on that. So these are key adjustment methods for correcting your PVT parameters to separator conditions. So I made mention of this, and in our hands-on, we'll be typing some of these equations, typing them, using them to correct them. And these are standard industry practice. And funny enough, back then we were in school. I don't know for us for now, maybe our schools now must have improved. But the truth is that most times in classroom setting, nobody will have time to teach you all these things. They expect you to know them. I don't know how the means by which they expect us to know, but they expect you to know these things. And some of us that we are privileged to even study them on our own, we didn't even see any practical relevance to them. So I think that's the whole idea. When it's time for us to do like a hands-on session, that's now when you will get to appreciate these equations, right? So I may not really touch it much, just the same way I didn't emphasize more on the trends, because we are still going to meet them at our hands-on session. But just to touch it briefly, we usually correct our BORS, right? There's equally one we correct relative volume, right? Now, that's where you'll be hearing things like Y function and the likes, but we are going to explain that in detail. So for correcting BO values, right, above bubble point, remember, the correction done at above bubble point will be different. Most cases will be different for when you are correcting below. Why? Because two different things are happening at those instances, right? Two different changes. And when we calculate area in mathematics, when we are calculating area under a curve, we usually take integral, right, with respect to something. So if you check that our either when you check RS or BO values, you notice that at bubble point, there is a unique change between the area by your right hand side and the area by your left hand side. And if you check, the shapes are not looking the same. One is looking like triangle and the other one is looking like trapezium or something like that. So it means that the formula you use for the right hand side won't be the same for the right hand side. That's equally what you are seeing here for correction purposes. So when you want to correct for above bubble points, you make use of BO, you multiply your BOFB. This is the bubble point bottom hole fluid. This is the bubble point oil formation volume factor obtained from your flash, obtained from your separator, right? You now multiply it by your VRED, this relative volume. And what's this relative volume? These are the individual volume we have in the PVT cell, right? Divided by the saturation volume. That's the volume at bubble point, right, at saturation point. So once you multiply this and loop it through across different VRELs, like different V relative volumes, you will obtain your BO, corrected BO. Then for correction of oil formation value factor, still the same BO below your bubble point, you are now making use of multiplying this one now by the individual BO values you have in your gotten from your differential liberation. You now divide it by the differential liberation bubble point BO value. So this is how you do it for below. Then for ROS, you have it this way. This is the one that was recommended by this is the one that I think Tariq Ahmed makes use of, and this is the one that McCain suggested, because some of the challenges with this one is that in as much as it serves the purpose, it can give you some error values, and we know that RS can never be error. And again, McCain had an argument around that this particular method actually lacks some physics-based answers and clarification. So him and some other persons recommended this, and so far so good. This one is equally good. But when we do a practice, you can equally see the practical difference. So just to walk us through this quickly before we can wrap up Another way, as I mentioned, source of PVT data is our black oil modeling. And thank God I was able to let us know that those correlations are just either they are regression based, whereby you gather experimental data, fit in some mathematical algorithms on them, and you're able to generate some equations as we'll be doing when we'll be doing the hands-on. You now generate, like, modify those mathematical algorithms to extract a correlation that can help you to make some estimates about our PVT parameters. So you see your BO, this for standing, I just use standing. We have many of them. We have standing, we have Glasso, we have Vasquez, we have Petrosky, we have Mahons and the likes. So, and too many of them. So for BO values, you can see some sample of what the correlation looks like. Okay, don't mind how it's looking like. All of them are just simple for you to understand, right? Then you are seeing Glasso correlation. This is it. You are seeing that this is the initial, the final formula, right? But this A, which is like a parameter, is a function of BOD, right? Then this BOD is equally a function of RS, your gas gravity and oil gravity and temperature. So it doesn't really matter when you are writing them in codes or typing them in function. They are easier written than understood, if I should say that. So for RS, picking, standing, and Glasso, you can see there are various correlation. So a good question now should be, does it mean why are they having the same dates for them? It wasn't a mistake. That's how it was done in their publication for Glasso. The same year he published for B estimation, if you check, it was equally the same year he calculated for RS, same for standing, right? So that's like a sample of our model, and this is what we'll be doing in our hands-on. So let me just touch this briefly. When we are doing the modeling, there are steps we use in doing the modeling, and if you are very, very creative with knowledge, you can easily transfer any skill we are going to teach you here for PVT to other areas, right? You can transfer it. At least there was someone that was working on his final year project, right? So I recommended a method, an approach like this. He used it, applied it, and was able to complete his thesis, saving him cost and everything. Come to think of it, everything was done with Excel that is readily available to everyone. So anything we are teaching here, you can transfer it to other domains. It must not be PVT. So, but let's understand how the PVT works. First things first, we plot lab data and make corrections. So we make plots of our data, and how we do it is that we plot the property or the parameter of interest, be it BO, RS, density, viscosity. We plot them in the vertical axis against the pressure. So this one now, the dotted one, you are seeing all these dotted lines are representing the lab. Then you now equally plot the correlations as well. And you can see how the correlation one, I think this thing should be red or orange. You are seeing it, then you see purple, you see green. So the idea is that if you are looking at this now, the one that looks closer enough to the lab points, dotted points, I think is the green one, right? So that's why, but others are far away from it. Now we need to match. And why do we do this matching? Why we are doing this matching is because of a problem. And what's that problem? Problem of globalization. So the correlations that we discussed about, all these correlations you are seeing here, we are done in non-Niger Delta area. We are within the Niger Delta region. Some of them we are done in California with different formation, reservoir formation, different reservoir fluid compositions and characteristics. So those correlations will definitely not perform well for our own case, right? That's why we need to modify them. We need to match those correlations to the data we have. And once we can achieve that matching, then we can trust that model for prediction. So the next step we now do is that we fit all correlation to the lab data, right? We now try to fit them, right? We now try to fit them by using, we can use optimization method, we can use any method at all. We just try to fit them. Then once we have done the fitting, and in mathematics optimization, we just need to find the difference between the actual and the predicted. That's the correlation. Once we have gotten that difference, which is obviously the error, right, we can now use any optimization method to minimize that error while adjusting our controllable parameters. And once we do that, we can now fit. That's how fitting is done. Then once we have done that, we can now select our best fit. So the industry practice questions can come around: which one should be the first one? If we have too many PVT parameters, which one should be priority? It depends on your experience and what works for you. But we usually start with the bubble point pressure. Once we have gotten the bubble point pressure parameter, PVT parameter, the next is to get your GOR, because any other thing you are going to calculate will be a function of your GOR, like your RS, right? Then from there, you can get your oil density, you can calculate your oil formation volume factor, you can calculate your viscosity. So that's why we have this diagram here. So as I explained to us, the problem around globalization and the rest, you can see the various PVT parameters and the correlations that we have, right? And you can see for each of these correlations, you are seeing the ranges of PVT parameters that we are used for, right? So when we do mathematical modeling, after modeling your system, you don't just give out that model to anybody to use. No, you must recommend the constraints, right? The threshold, or like the boundary where your formula will work, so that any system someone is trying to model that is outside that, the person needs to modify, right? So for glass toner, you are seeing that it works for bubble point pressure 167 down to 7,142, then down to Mahomes. So you are seeing their individual parameters. That's why it's always good when you want to make choice and selection. Always consider these trends or these thresholds and see whether they are best fit for your crude oil sample that you are trying to model. So in summary, the workflow for PVT report analysis, that first of all, and this is the workflow we'll be adopting in our next practical session. We first of all do some data extraction. And why are we extracting? We are extracting the data because PVT data doesn't just come in Excel format. No, it comes as a PVT report. So we read, understand the PVT report, extract the necessary data that we need, or all the data that we need, then do some adjustment, those corrections that we talked about, correcting the DLE to the separator condition. Once we have done that, the next thing we do is to do modeling, do PVT black oil modeling using the various parameters that the various black oil correlations that we have talked about. And once we have done that modeling, the last stage will be to fit the correlations. Once we have fit them using any optimization method or fitting method that we deem fit, then we can now select the best correlation and use it for estimating more PVT parameters, which will now be used for modeling systems and performing other reservoir engineering calculations. So I think the up next will be for our practical session, which will not be today, but in subsequent time. So at this point, I'll be expecting questions, and while I hand over to Blessing. Thank you so much for listening.
Okay, Chris, thank you so much for this wonderful section. Thank you so much. So wonderful. Okay, this is the time for questions. So if you have any question, you can indicate by raising up your hand so that I will call you. Thank you. Please let's ask question. We've learned a lot today. So if you have question, okay. I can see one hand up. Rufus, please ask your question.
Okay. Hello, good evening.
Good evening.
Thank you so much. Okay, I want to ask to be sure I'm not lost and I'm also on point. Does in does pressure does the pressure affect activity?
Does pressure affect PVT?
Or should I say, what's the role of pressure in calculation for activity? Activity.
Okay, you're asking of the role of pressure in PVT calculation. Okay, is that your question?
Hello, can you hear me?
Yeah, I can hear you. Is that your question? Praise.
Okay.
Yes, that's it.
Okay, Rufus, thank you so much for that question. When I started by trying to uh, bring us back to our Boyle's law, which states that as far as temperature is kept constant for any volume of oil that we have, right, any volume of fluid or gas that we have, the pressure applied to that volume is inversely proportional to the volume, right? So there is a pressure volume inverse relationship. Okay, so that alone tells us that whenever there is any change in our uh, whenever there is any change in pressure, our gas dissolved in our oil will respond to that change. So invariably, pressure affects all our crude oil sample. If you are dropping the pressure of our crude oil sample, you notice that gases will have more spaces, right? If you review our kinetic laws of motion, so you notice that as you are dropping the pressure, the volume will increase. So the gases now will now have more spaces to hit each other and exhibit kind of elastic collision, right? So pressure affects our PVT parameters. And if it doesn't affect it directly, it can affect it indirectly through another source. Why I'm saying this is that there are some correlations that you will see. You are seeing a PVT parameter, a function of other parameters, but you are not seeing pressure in that equation. So, but all those individual parameters, right, are equally dependent on pressure. So pressure, to answer your question, pressure affects all our PVT parameters. So Rufus, did I
Uh,
answer?
Rufus, is your question being answered? Okay. Any other question, please indicate by raising your hand so that we can call you. All right, Victor, yeah, you can go ahead and ask your question.
All right, thank you, Blessing. Thank you, Praise, for the wonderful presentation. I appreciate. I quickly want to ask, in terms of doing the adjustment from the chart to follow the initial or the laboratory experiment trend, you made mention of optimization. Do do we have is there a specific optimization level to which we can optimize to, or we just do it from our initiative? For instance, we let's say something like a plus or minus two or this that's what I mean.
Okay. Okay. So, although my network was a little bit bad, but just to provide answer to that, when we say optimization and when we say we are trying to fit something, we usually have some threshold. Okay. So the idea is that we want to reduce the error, right? The error, which is the difference between the actual, like the lab, and the one the correlation is giving us. We want to minimize that error as small as possible. So if I want to answer it this way, I can go ahead and tell you that in the industry, we usually appreciate working with PVT parameters or PVT black oil models that are having error values, let's say below or within the range of 5%, but not above 8%. However, I still need to point out this error that we are trying to manage or tolerate. You still need to be careful. What is the PVT parameter you are talking about? If your goal is BO, RS, these are critical parameters. You don't just joke with them. So you must make sure that the error for them are as small as possible. Okay, so there's equally guidance in the amount of work you are putting in for your optimization, just like the example I gave you, roughly 5% or at most 6 to 7%, that's tolerable for industry practice.
All right, thank you.
Okay, you're welcome.
Okay. All right. Thank you, Praise. Patient, please, you can ask a question.
Okay, good evening, and thank you so much for the presentation. I would want to ask two major things. The first would be, is there a particular reason why mercury is used to try to get that pressure you want on the oil? Is there no chance that there might be some kind of reaction and then it affects your result? So I want to know if, as in using mercury is like a standard and it doesn't have any way of infusing some kind of error in the result. And then second would be that's the last table you talked about where we had various, we had, after you gave the 3 methods of, where you talked about correlation and trying to have a uniform graph or something, there's a table underneath where you give the different ranges for different authors also. I didn't quite get that clearly. What does a range for this author signify? Why would I use the one for this person and not use the one for the other? Thank you.
Okay, so thank you so much for that question. So let me just quickly share this now. So for your first question, you can see my screen, right?
Yes, I can.
Yes.
Okay, so for your first question, where you were asking about mercury, so when I was explaining, I explained that it must not be mercury, so it can be nitrogen, right? So it can be nitrogen. However, things are done with reasons. So most times, depending on the pressure you are working on, right, we have already determined the pressure conditions that these gases or these elements we are using are tolerable, right? So we already have determined the pressure conditions this either mercury, either nitrogen can work, right? So that alone influences us. So mercury now can be used for pressures that are within its range, right? Nitrogen, at times, we equally use nitrogen for providing the same pressure, especially when we are going at higher pressure conditions. For example, when we are doing downhole sampling. So you notice that bottle we are using, that setup we are using to collect fluid sample from the subsurface at high pressure conditions, we make use of nitrogen in areas like that. So it doesn't really we have already done those estimates and know that it won't influence or mix up or react with our crude oil sample at those possible pressure ranges. So I believe that handles that. Then for this one, let me just run through it again. I was trying to explain that these things you are seeing are PVT parameters, right? Where you have bubble points, temperature, and the likes. Then these are various correlations. Now, for each correlation, they have their tolerance, they have their PVT ranges. So for GLASO now, this 165 to 7,142 is informing you that GLASO from research, from experimentation, has proven to be very competent and very good in working by estimating bubble point pressures of this range. So it means that anytime you are trying to estimate bubble point pressure that is outside the range of 165 to 7,142, it means that GLASO won't be a good option for you. That's the same thing across other PVT parameters, temperature, formation volume factor, gas oil ratio, across all the correlations that you have. Okay, so I believe that must have answered that as well.
Yeah, sure, that's clear. It's clear now. Thank you.
All right, you're welcome.